Hi everybody, my name is Rodrigo Ochoa and today I will present this poster called pyPept, a Python library to generate atomistic representations of peptides. So I am part of the computational chemistry team in Berlin Ingelheim, Biberach, Germany. The main motivation of this work is related with the BILN format, is a line notation that has been developed to have a human readable notation to describe complex peptides. So this format allows different kind of searches, comparisons, and analysis with peptides to generate canonical representations. In this table, you can see different examples using a linear peptide or a peptide with a disulfide bond, a cyclic peptide or a branch peptide. So this format can be also converted to the Helm notation, as you can see here in this example. But probably one of the main requirements for us is to manipulate and to generate molecular objects from this format. So given that with BILN we can run, we can do MMP analysis or calculate peptide properties or SAR interpretation. So we developed this package called pyPept to allow running this analysis and interconvert between the 2D representations and 3D conformers using the RDKit package. So pyPept in general is a self-contained Python package to read peptides using the bin format and a monomer dictionary that I'm going to explain. And generate, as I mentioned, these 2D and 3D representations. The code is open source available through the BI GitHub repository. Regarding the classes, so one of them is the sequence.py that basically allows reading the peptide through the monomer dictionary. And when I talk about dictionary, it's basically a representation of each monomer where we highlight the R groups involved in the generation of bonds between the monomers. And it can be done not only for natural amino acids, but also for non-natural residues and capping groups. So to create the dictionary, we use the Helm monomer repository available in GitHub, where we have information about the SMILES of each monomer, and also we can highlight which type of residue it is and the atom indices read by the RDKit internally. Then with the molecule.py, we connect the monomers and we assign the correct bonds to the RDKit object. And with the RDKit, we can generate also the 2D representation where the 2D dihedrals are fixed to have a clean image of the molecule. And for that purpose, we have two methodologies. One is an in-house protocol, and another one is a module available in the RDKit. However, there are exceptions like hepcidin. Here you can see is a large peptide with 4 disulfide bonds, and using private or public the pictures in general is quite difficult to represent, but at least we have internally an RDKit object with correct bonds, and it can be used for further analysis. And one of them is provided with the conformer.py class, where we can generate the conformer by the addition of secondary structure restraints. And for that purpose, we developed a secondary structure predictor by comparing fragments of the peptide, of the query peptide, with peptides having 3D structures in the PDB. And for that purpose, each residue will be assigned a category of secondary structure, in this case a helix, sheet, coil, or a turn, based on a profile with the most frequent elements detected on the PDB. And with that, we can obtain a PDB file with correct residue and atom assignation that can be used later for simulations or for another kind of predictions, not only with natural amino acids, but also with non-natural residues. Finally, here I'm showing some examples One of them, here, contains 2 capping groups. In the second example, we have 3 different non-natural residues connected with natural amino acids. And in the third case, we have a peptide, a branch peptide with a lactam bond between the lysine and the glutamic acid. So the code provides a list of monomers that can be embedded, including the capping groups. For the secondary structure, normally what we do is that we use natural analogs of the non-natural residues to predict the secondary structure and then assign the correct dihedrals. And finally, the format allows us also to include branches and other chemical extensions if we want to increase the peptide complexity. So again, the code is open source, and any questions you can write on my email. So thank you very much for your attention.